Chapter 15, Lesson 1. In this chapter we'll talk about something called equilibrium, a very important concept that will carry us through a good portion of this second semester. Now, we'll begin by giving a little example here and making the statement that there's a big proportion of reactions in chemistry that actually occur both in the reactants to products direction and products to reactants. They actually occur in both directions. So an example here, N2O4 becomes NO2, essentially breaks down, decomposes into two NO2 molecules, but at the same time NO2 can form back into N2O4. And the example of this is, here we have a little vessel, glass vessel, with some N2O4 in it, and NO2 actually, both of them are present here. And depending on the temperature, we can increase the amount of NO2. That's what you see with a hot beaker here. Or if we cool, there's a bunch of ice in here, we can actually decrease the color. So what you see is we're able to switch the reaction from products to reactants and back to products, is kind of the idea. And we're going to be taking a look at this class of reactions, these reversible reactions. Now, to lay the groundwork for this concept of equilibrium, what happens is, as the system approaches equilibrium, equilibrium has to be approached first, or has to be attained. What happens is both the forward and reverse reactions are occurring. And when you get to equilibrium, the two reactions occur at the same rate. So with these systems, the chemical reaction never really stops. It actually keeps occurring. It's just that the forward rate and the reverse rate equal out. And we'll take a look at this idea here in a second. So this is back to our first reaction. If we measure how NO2, this is the brown gas, changes as we go toward equilibrium, first of all we begin with a very small amount, but then as the reaction proceeds, NO2 increases, and then there comes a point at which it stops increasing, it stops changing, and this portion shows that we have a constant amount of NO2 present, and this is the point at which equilibrium is reached. So at equilibrium, the reactions keep going, the reactants still become products, the products still become reactants, but the amount or the rate has equaled out. So to make a big statement, because we have both the forward and reverse reactions happening under equilibrium, we will depict this using a double arrow. Actually, we have two half arrows. It's a bit harder to see here, but what we mean is we'll put two arrows like this. Sometimes we'll also use just a double-headed arrow, although this means something different. This actually refers to something called resonance. So usually the best way to depict it is using two half arrows, as is done in this example. So we're going to, the major idea here will be something called the equilibrium constant. And much like we had a constant in the previous chapter, in the rates chapter, we will have an equilibrium constant here. So if we write the forward reaction along with its rate law, and this is from chapter 14, we'll see that the rate is proportional to the concentration of N2O4. N2O4 is first order, if you recall. And then we can determine the constant. This would be the constant of the forward reaction. That's what that little F stands for. We can then likewise do for the reverse reaction. We can say, well, our products are now turning back into reactants, so we can rewrite this equation and derive a rate law for it as well. And we can say this constant is the constant of the reverse reaction. And now what we'll do, because we said that at equilibrium both the forward and reverse reactions equal in rate, in other words, they don't stop occurring, they just occur at the same rate, what we've got is we can take the two rate laws, because our two rates are equal at equilibrium, and make them equal to one another. And then what we can do is we can take and solve and combine our k's. So in this case I'm going to actually divide by kr on the right side, and likewise on the left side. These cancel out, and we get ourselves this final equation. So we get a ratio of the two concentrations. These are the product concentrations, and these in the denominator are the reactant concentrations. And these two concentrations then decide or define the equilibrium constant. So usually this is depicted with a big K, capital K, with an EQ for the subscript, and it is really the ratio of products over reactants. Now the interesting thing here is you can actually derive the equilibrium constant from the balanced equation, as opposed to, if you recall, we could not know the rate constants directly from the balanced equation because we had to perform an experiment to determine the rates and how concentration affects rate. But with this chapter, KEQ can be known just from the balanced equation. We can define it, in other words, and that's what we do here. So this is a generalization for the equilibrium constant. Your constant is equal to, notice here we have C and D for our products. The products will go in the numerator, here they are, C and D, raised to the power of the coefficient. Notice here the C and the C and the D and the D. And then the reactants, likewise, will go on the bottom in the denominator, raised to their coefficients. The power then will be the coefficient. So Kc, now this little c actually stands for something. The c refers to concentration. And you can define K in terms of different things, in terms of different quantities. Recall that if we have these brackets mean we have molarity as our concentration. So we can define it in terms of pressure, as we'll see in a minute. But it'll, in general, K in general should be thought of as products over reactants. Products divided by reactants is the idea. And looks like we have a little more to fill in there. Okay, why don't we do a few example problems. We want to write the equilibrium expressions for the following two reactions. So in reaction A, we're going to do essentially products over reactants. Let's go ahead and do, in this case it's going to be Kc. Because it's Kc, we'll have to use the brackets for concentration. Oxygen, so if you recall, K is defined as products over reactants. So oxygen is our product. We'll go ahead and put oxygen in brackets here, and it's diatomic oxygen. And then we'll raise oxygen's concentration to the third. And then at the bottom we'll put the reactants. The reactants we have O3, this is ozone, in concentration squared. So this is how we will define Kc. To get the equilibrium constant, we'll have to know the concentrations of both O2 and O3 at equilibrium. Let's do the same thing for part B. To get the Kc for part B, we'll again do products divided by reactants. Our products in this case is NaCl, concentration of NaCl, squared, divided by the concentrations of NO, squared, multiplied by the concentration of Cl2. So you would multiply your reactants and your products together. And this is how this one's defined. Not too bad. Now, the other way of expressing the equilibrium constant is in terms of pressures. So anytime you have a reaction that's composed primarily of gases, it's much more convenient to express it in terms of pressure. So your K will have a sub P on it, K sub P. We have the same exact thing. We have now the pressure of your products divided by the pressure of your reactants, and to the power of their coefficients still. So nothing really changes. The measurable quantity here, instead of being concentration, is now pressure. Now Kc and Kp for a particular reaction are related because we could, say if we have gases, if we're working with a gaseous reaction, we could express that in terms of concentration. We couldn't get the molarity of a gas. That's not impossible. And there is a way to convert the two. So the relationship between Kp and Kc is actually given down here, and we're actually going to use the ideal gas law to derive this. because Kc, if you recall, deals with moles over volume, over liters, and in PV/nRT, or the way that's related to pressure is through PV/nRT. We have both moles and we have volume. So we're able to relate it. We won't derive it here, but there's a way to derive it and get this relationship. And here is what the relationship says. Kp equals Kc multiplied by RT. This comes essentially from the ideal gas law, raised to the power of delta N. And down here we have the statement that delta N is the change in, means final minus initial. In our case, it's the products minus reactants. So we take the moles of gaseous products minus moles of gaseous reactants, and we'll be able to get our delta N. So why not try an example? So here we have synthesis of ammonia from nitrogen and hydrogen. We're given a balanced equation, and we're given the Kc for the system. And because most of these are gases, it's much more convenient to define Kp. So why don't we go ahead and solve for Kp in terms of Kc. So if you recall, our reaction, or our equation, said that Kp is equal to Kc multiplied by RT to the delta N. So at this point, it's a matter of just plugging in the values and solving for the equation. So Kc is given as 9.60. Now notice that Kc does not have units. Customarily, we don't include units with Kc, with most equilibrium constants. We could derive them, but usually that's not done, so we will leave it off here. We won't worry about the units. So we got 9.60. R is the gas constant, and if you remember, it's 0.0821 for 3 significant figures. Liters, atmospheres per mole Kelvin. Multiplied by temperature, in this case 300 degrees Celsius. We have to add 273. Because our gas constant is in terms of Kelvin, we'll have to make sure that our temperature is also in terms of Kelvin. So 300 plus 273 gives us 573 Kelvin. And that's what we will put for the temperature. Now it's important actually that this whole product here is in brackets because we first have to multiply the two and then we take it to the power. In our case, the power, the delta N in our case, will actually be moles of products minus reactants. So we have 2 moles of gaseous products. We have 3 plus 1. We have 4 moles of gaseous reactants. So we have 2 minus 4, which gives us -2. And it is definitely possible to have a negative value for delta N. And what this would mean essentially is that it's this value squared on the bottom of the denominator. So let's go ahead and multiply these together, and let's see if we can come up with a value that we agree upon. Let's go ahead and plug this into your calculator. Raise it to the power. And we should get ourselves a value that looks something like this. 30452 with 2 significant figures. Or, using scientific notation, 4.52 times 10 to the -4th. And no units. Do not worry about the units here. And that's how Kc is related to Kp. We'll wrap up the discussion with asking the question, or stating the fact that equilibrium can be reached from either the product or the reactant direction. What we mean here is, because we have a system that's in equilibrium and both processes are occurring, it doesn't really matter where we start. We could technically begin with products and then end up with reactants. So what they show you here is that if your initial concentrations are 0 for the reactants, this is, if you remember, this is our initial equation, that's N2O4 in equilibrium with 2NO2. So NO2 is actually our product. So notice we're not starting with any reactant at all, we're starting directly with product. You will still find that the equilibrium concentrations contain both, and the ratio of these will still be the same. Notice the ratio of all these. You can also begin with all reactants and no products, and still your K value will be the same, roughly the same. So the ratio remains constant even though you begin with a lot of reactants, not many products, or the other way around. And this shows the same idea graphically. So if you take a look, these two little graphs show us beginning. So in this case, the reaction is a little different. We have N2, H2, and NH3. And notice here we begin with 0 of our product and a lot of our reactant. And then in the second graph, we begin with 0 of our reactants and a lot of our products. But at the end of it, the ratio is exactly the same in both cases. So the proportion of the three substances is the same, is the idea. And we're going to finish up with a discussion of what this value actually means. So K, this equilibrium constant, again remember it's defined as products divided by reactants in general. So this gives us the ratio of products over reactants, which means if K is a very big number, this means we have a lot of products and not many reactants. That means we can say equilibrium lies on the product side. As you see here, we have quite a bit of products and not much reactants because the number at the top is big, the number at the bottom is small. And this is called a product-favored equilibrium. If, on the other hand, the equilibrium constant turns out to be very small, we could say that this is a reactant-favored equilibrium. That's because, again, K is defined as products over reactants. So if K is a small number, that means the top here is small and the bottom is very big. We divide by a big number, and in the end we get a small number, which means we have a lot of reactants, a big number of reactants, and not much of products. That's the idea. So this is how we decide whether or what this value of K means. We're actually going to do some calculations in the second lesson, but this is in general, qualitatively, what we mean. So let's wrap up with this example. It says the equilibrium constant for this following reaction varies with temperature, and this is true. All constants, most constants will vary with temperature. That's why usually temperature is given along with an equilibrium constant. So the question is the formation of HI, that's our product here, favored more at the higher or at the lower temperature? And we see that the Kc at 794, I'm sorry, Kc is 794 at 298 Kelvin. This is roughly room temperature, 25 degrees Celsius. And Kc drops down to 54 at quite a bit above room temperature, 700 K. So because Kc is higher at a lower temperature, recall that Kc is products over reactants. Because we have a higher Kc at the lower temperature, you'll form more product. In this case, our product is HI. You'll form more product at a lower temperature. So you want to run this reaction at low temperature if you're hoping to produce yourself some HI. That's the idea. So we can analyze the equilibrium constant and from it determine the conditions under which we must run a reaction. That completes for us lesson 1 of chapter 15.